Okay, let us come back to so in the ultimate case. So I showed you now how to reconstruct this very simple and first one-dimensional profile, which was of course I raised lots of problems without telling you how to solve. I promise I will tell you, but at least just to be aware of the problems we are facing. So till now we considered, at least in principle, how can we reconstruct such a profile. I have here epsilon naught, I jump to epsilon 1, and I come back to epsilon naught. So here is 0 and here x1, and this is a profile I am willing to retrieve or to reconstruct. Two unknowns, this is the width and the height. That's all. Two unknowns, we created two equations with measurements. I raised the difficulties related to the solution without giving you any idea about how we solve. But at least now we classified the different cases. We may have linear relations. Our concern will be to guarantee that the linear relations are independent. Even if we have independent relations, but the case is nonlinear, we may have no solution, we may have multiple solutions, we may have infinite number of solutions. I didn't answer this yet. I just told you, if we decide to work numerically, like the majority of the community, of the imaging community, we should understand what's behind. And starting from now, I will switch to simplifying the situation so that we can have a solution, a unique solution. And if you are not content with the accuracy of this solution, because now in order to have a solution, we have to simplify. And as we simplify, we depart from the actual image. You simplify here and there and there, and as you simplify more, you are far away from the reality. But this is very important for you, especially for young people like you, to understand that what you learned in the university is, in general, simplification. No practical system, no practical work has direct something to do with what you learned. It's only simplification in order to understand, but the real world is different. It's exactly the same issue. We have it here. Again, I will, when I am done here, maybe the next 5 minutes, I will simplify the problem. My goal is to have a situation, have a solvable situation where you can say, okay, now I have a solution, but keeping in mind that this solution may be far away from the real image. It is just a rough image. Now you have two possibilities. Either you need in your application what is called qualitative imaging. Qualitative imaging, oh, is great. Qualitative imaging means you really don't need to know how much epsilon 1 is. All what you need to know is whether to distinguish between two different layers, to have rough estimation how thick is this layer. Let us take say medical imaging. In medical imaging, just let me give me 2 minutes just to prepare here. Thanks. I think it should be connected from here. Can you read from here? The advantage here that everything will be saved to PowerPoint and you can have it. Okay, back to our discussion. If you just need qualitative imaging, which means you are not really interested in the real values, like if you are performing medical imaging, just to distinguish between liver and maybe stomach or tissues here or there, or especially if you are within the framework of a diagnostic, distinguish between healthy cells and male cells and all these things. In this case, you really don't, you are not really looking for a quantitative imaging in which you say exactly epsilon1, exactly x1, and so on. If x1 here, thickness of a layer is a little bit less, a little bit more, it is not so important. In this case, the simplified theory, which I'm going to present now, is enough. We will perform some simplifications, and we will see that using these simplifications, we may have an image uniquely. I will, of course, discuss some artifacts. Artifacts are defined as anything which doesn't belong to the image, but you see it nevertheless. This is called artifact. In the community, in the imaging community, describes anything which disturbs the real image and doesn't really belong to the image. This is so. Within the framework of our simplification, we will understand what are artifacts, what are the sources for creating artifacts, how can I define resolution, how can I distinguish between, within the resolution, distinguish between two nearby points, what is contrast. So we will deal with the fundamentals of imaging within the framework of this simplified theory, assuming or taking certain assumptions into account. In case you are looking for quantitative image in which these values are really needed, and I must admit this is very, very seldom, very, very rare that you use imaging in order to measure, in order to find real values. But nevertheless, if it is needed, in this case, we will take our rough image, our approximate image, as the initial points, which I showed to you in the last discussion. I told you we will have multiple solutions. We must, in order to converge and to catch the actual solution or the real solution, we must be as near as possible. So in this case, we will follow two-track strategy. The first track is to have an initial guess, a rough image, which I will use afterwards, together with an accurate simulator, iterating 2 or 3 times until I have the real, accurate, quantitative image. Agree on that? So we discussed the problems related to numerical analysis and numerical simulation and so on. We know the problems which we have, and I hope that with this here we will answer the problem. You raised many problems, but you didn't tell us how to solve. Now we have an approach for solving that. We will simplify. From this simplification, we will be sure that we have a solution and a unique solution. We take this unique solution either to use it as it is in quantitative imaging or to take it as a good initial point for an iterative algorithm using accurate simulator, which will end up in the real image. Okay. Let me switch this off here. Okay, the approximation we are going to assume or to adopt is called small reflection assumption. I will start by a number of stratified, a number of layers with unknown thicknesses and with unknown dielectric constants. The first case is discrete case, in which the thicknesses of the layers are finite. The number is still unknown, but the thicknesses are finite, so that I still have step function, stair-step function. It is not a continuous profile, but it is something like stepping. It's exactly like a continuation of what we proposed before. So we will have something like that. This is x, and this is here epsilon 0. This is our profile. So we are going to reconstruct something like that. We don't know x1, x2, x3. We don't know also up to which x it does go. And we don't know epsilon 1, epsilon 2, epsilon 3, and so on. This is our target. The small reflection assumption is simply formulated as, at each of these interfaces, as long as I don't have step, I don't have interface, real interface, waves will propagate back and forth. At each interface, we will have a local reflection coefficient. The assumption itself is simply formulated as, if you start by 1 here, you will have a tiny reflection, and therefore it's called small reflection, something which is much less than 1 as a reflection coefficient, at the interface between free space and the first layer. The transmission afterwards is, in principle, if you are incident with 1, magnitude 1, is something less than 1, maybe 0.999. If you have very, very weak reflection. I will assume it 1. So I will never assume that the transmission is less than 1 from the magnitude here. So this one will propagate up to the next interface. We'll have a tiny reflection, again because it is small reflection, but it remains 1 as transmitted. Any of these tiny reflections, when it goes through one of the previous layer, it doesn't experience any reflection. So it will go directly. Of course, the multiple reflection means that between here and there, between x1 and x2, If I come here, I will have small reflection. This small reflection will go back, back, back. I will assume that it goes without any attenuation, because if it is here, say 1%, and I have another 1% here, now I'm very, very small, so I will neglect this multiple reflection, and I assume first reflection, and then go second reflection, and then go third reflection, and each of these reflections are going without any further reflections, just once. Because every further reflection, each further reflection is multiplication by another small number, and this small number, if you have 1%, you have now 10 to the power minus 4, and so on. So this is the only assumption I'm going to adopt. And based on that, we will have a very, very nice expression for the total reflection coefficient, and from which we can retrieve the profile, at least in principle. Okay? Good. Because what you really retrieve is not the distances. You remember in the exact expression, we had theta. And theta was a product of the wave number within the material times the thickness. And you have it always as a unit. So you cannot separate, at least now in terms of what you receive as a reflection. You cannot separate. So this means within a layer, we have the thickness, say, let us call delta x. If we deal with the time delay, not the thickness, let us deal with a time delay. A time delay, if a time delay is multiplied by omega, it gives you delay angle. So we have theta, we have x, and we'll introduce also t, a time delay. We know that delta theta is simply the propagation constant k times delta x. You multiply the wave number times the distance. This is the delay angle between one interface to the next. But at the same time, it is omega times delta t, where delta t is the real-time delay. Okay? Because omega is known, so whether you know delta theta or delta t is the same, because omega is in your control. But because k itself, if you look to the expression of k, it is omega square root of mu naught epsilon naught epsilon r, and you are looking for that. So epsilon r now is hidden in the local reflection coefficients and also in k. In other words, it is also, you cannot distinguish directly between x and epsilon r. So therefore, within the framework of our approximation, we will try first to find out the epsilon r profile in terms of delta t. So the thicknesses of the layers are not the real physical thicknesses, but these are time differences, time of flight. Delta t in this case, it is a time of flight of the plane wave from interface to the next interface. This is delta t. Okay? And in a next step, in a second step, we will try to find out how can, using the epsilon r profile we know, how can we find out the delta x's from the delta t's. The sequence of our approach is clear. So in this case, I will first say I have now the profile, it is a function of t, not a function of x. And I have now, this is epsilon naught, and I have t1, t2, t3, and I will tell you This is epsilon r of t. So t2 minus t1 is theta 2 minus theta 1 divided by omega, which is, what was theta between, if this is here epsilon 1, this is epsilon 2. So we are talking about the difference between T2 and T1. So we have here K2, because this is the medium 2, times x2 minus x1 divided by omega. But K2 itself was omega over c. So we can say it is omega square root of epsilon 2 times mu naught, this is K2, times x2 minus x1 divided by omega. So we have here omega with omega. So we will have it actually as square root of epsilon 2 mu naught in x2 minus x1. Just to rewrite the relations again. By the way, you don't need to write with. Everything which I write here will be put in a PowerPoint, and I will give it to you. So you don't need to lose. Just concentrate with me. Only if you see something which is not clear in my writing, just let me know so that I can correct it now. Okay? So again, just to make things a little bit fine, if you look to epsilon 2 is actually epsilon r relative times epsilon naught, and square root of epsilon naught times mu naught is 1 over c naught. So we can write down this as c naught, and here square root of epsilon 2 times x2 minus x1. So this is actually the relation between
epsilon 2 mu naught.
Epsilon r. Sorry. Epsilon relative.
Relative, no?
Yeah, the relative. In order just. Okay, this is actually what we. Let me make it in a box. And this actually applies after. I will show you maybe still today how to write down a very, very simple matrix equation. If we have the t's, we can immediately find the x's. But it's important first to work in the time domain and not in the x domain. In the time is interpreted now as time of flight. The time of flight needed from 1 to 1. Clear? Okay. This is the first assumption, first approximation, small reflection, which means we don't have a high contrast. The approximation itself is also named low contrast approximation. So you may find it in the literature as a low contrast approximation or small reflection approximation. Okay? So jumping from one dielectric constant to the next, from one layer to the other, is not really very, very strong. Again, my measure for whether it is strong or not is again the local reflection coefficient. If I have here epsilon 2 and here epsilon 1, so the local reflection coefficient, which is 2, 1, is Z2 minus Z1 divided by Z2 plus Z1. This must be much less from the magnitude than 1. This is the only thing which we need. Now you can express Z2 and Z1 in terms of epsilon 2 and epsilon 1 and so on. We would like to have it in the order of magnitude 1% or something like that. This is actually our approximation. Okay? Of course, you may do the following. You can, and this is legitimate, you can assume first that we don't have strong contrast. And apply the theory until you find the contrast, and look to the until you find the profile, and look to the profile. If you find out that there is also known in the literature as a zeroth order Born approximation. There is what is called Born approximation. This one here is the very, very first approximation. You may now take this profile, okay, and use it as an initial profile. So by taking the profile itself and considering the multiple reflection within it, so as an exact, at least now I have an idea about how many layers, rough estimation of the thicknesses, rough estimation of the values of the dielectric constant, and so on. Now I can take this initial structure, calculate the actual reflection coefficient by assuming multiple reflection, or by applying what you know, how to transform an impedance along a transmission line from layer to layer to layer to layer. So you can write down a very, very simple MATLAB program for that until you find now an expression or a program. Expression or program is the same, because in an expression you put the values and you get the reflection coefficient. A program, you put it as input parameters, and the program gives you the reflection coefficient. So when I say expression analytically derived, or I say a program, MATLAB written by you, or CST written by somebody else, it's actually the same. In all cases, it means direct problem. Direct problem, I know the topology, I know everything, and I calculate the reflection coefficient. Okay? This is a direct problem. Good. You may take this and refine it, which means now start to change a little bit, according to a certain strategy, of course, start to change a little bit in the values of epsilons and the values of the thicknesses, until the expression itself and what you measured are very near to each other. This discipline, or this type of calculation, belongs to optimization. I can imagine that some of you have were already involved in optimization. You have lots of optimization routines. Why it's called optimization, for those who are not acquainted with that? In optimization, you define what's called cost function. Cost function is something like averaging the difference between measurements and simulation. Okay? Why it is cost? Because it was initially invented or proposed by the economic people. They wanted to minimize costs. So if you have measurements, say measurement vector, which means say measurements at different frequencies, and you have corresponding values from the simulator, from your expression, whatever. So you define the difference between measurements and simulation. And average, say, as a function of frequency or a function of time. So it depends, depending on the situation, and try to play with the parameters you are looking for until this minimum, this cost function becomes minimum. This is optimization. I can imagine some of you were already involved in this. Okay. Yes.
T2 minus T1 is not dependent on frequency?
Let us, therefore I wrote this. Look, we assume plane waves. And within this, the framework of this assumption, we know that the propagation constant is directly proportional to the frequency.
But in this expression,
omega why? You have c times t is distance, but it is weighted distance. It is not wrong. So you slow down, because look, for plane waves, of course, if you are working in a waveguide where you have dispersion, is something else. But now for our case, we are dealing with plane waves, which means that the propagation constant is directly proportional to the frequency. or K is omega divided by C. So what you see here, it tells you that if you multiply C naught by T divided by square root of epsilon r, this is actually the distance, okay? Or it is a weighted distance because with higher epsilon r, you slow down the electromagnetic wave. So this is a slow down factor, the square root of epsilon r. But in direct problems, you never thought about it because you know it. But in inverse problem, you look for it. Therefore, you must take care of it. But for you now, what is the relation between flight time and thickness is clear. Right? Yes?
Distance from 0 is reference.
No? Yes. So that the thicknesses, let me. So I think I put it here. x1, x2, x3, so that the thickness of the first layer is x1 minus 0. Say 0 is x naught. The thickness of the second layer is x2 minus x1, and so on. Clear? Okay. This is the first assumption. The second assumption, which I'm going to adopt, is I will have a more fine subdivisions. So if you are expecting now delta t in the order of magnitudes of, say, milliseconds, I will go much behind, and I will assume picosecond. It is first, say, thinking experiment. So that I will subdivide this as an experiment in my head, and we'll see why. Subdivide the entire range into much smaller steps. So say, but everyone has a thickness of delta t of much smaller. My purpose here is to have a unified subdivision, because the original problem, of course, we don't know. We haven't imaged yet. So we don't know whether delta 1 is equal to delta 2 or something like that. So I would say let us subdivide much more fine, which means we will subdivide equally by small delta t. And we will assume that at each of these introduced delta t, there is a local reflection. In case you have it, it is there. In case you don't have it, it is zero. So in other words, let me say the actual, say here this, so say this was delta t, and we have, say, delta t2, but these small delta t's are still there. So we may say now, at this interface, I will assume that we have really much more layers. We have a layer here, there, everywhere. And within the framework of our assumption, we will say, if there is in reality a layer there, I will have a local reflection here. If not, I will have zero, so because it goes here without reflection. But I will assume first that at every individual thin layer, there is a local reflection. Okay? And from my result, I will see. Maybe here it is 0, 0, 0, 0, 0, and then 1 or 0.1 or something like that. This will come to me later. But now the next assumption. Till now, how many assumptions have we made? So first, the low contrast. And this is here not a real assumption. This is just a way of thinking. I will bring as an approximation, I will bring a real reflection to the nearest subdivision. Because if you have delta t, imagine that this is, say, 1 millisecond. and this is here 1.345 second, or 35. So the millisecond is not accommodated here. So you will look now for what is the nearest delta t. And you say, okay, the actual reflection takes place not at this one, but at the nearest delta t. So that I have a unified picture. I have multiple layers. At each sublayer, at each interface between two successive layers, all layers have the same thickness. Small delta t, delta t, delta t. Not the big delta t's, the small delta t. And I will assume I will have reflection at each one. If the actual reflection is there, I'm fine. If there is no actual reflection there, it is 0. If the actual reflection is a little bit right or left, I will approximate it as if it were at the nearest interface. Clear? Okay. Starting from now, I will assume that the following picture. I have now equispaced layers. So this is, each one is delta t, small delta t. Okay? And at each interface, I will assume a local reflection. If it is there, it is there. If not, it is 0. And I will number this reflection. I would like to make it a little bit systematic. I will number this reflection. We have here 0, 1, 2, 3, 4, and so on. Because we are not going to deal with multiple reflection, it has no sense now to identify the local reflection coefficient by two indices. Because in the past we said R10, R01. I will just use just one index, which means, let me take this nice color here. So I will have here R0, here R1, here R2. So as you see, from 0 to 1 you have R0, from 1 to 2 you have R1, and so on. Okay? Good. Next, let us try to find a simple expression for the measured reflection coefficient. So I will have here something like that. This is 1, this is R. This is here 1. I will say, denote the total reflection coefficient measured in the free space with R bar, in order to distinguish this from the local reflection coefficient without bar. We'll quickly see now that they are Fourier transform pair. But let us now identify the local reflection coefficient as R0, R1, R2, and so on. And what we measure in free space back to the first interface, we call it R bar. Let us now try to find a simple expression for R bar. What is R bar? It is a summation of small reflections. Let me assume, I don't know the number yet, but let me assume that the total number of my sublayers, these small layers, is n. So I will sum from 0 to n minus 1, because I start by 0. And I have a local reflection R0 without any delay. R1 will have a time delay twice delta t, because 1/4 and 1 back. R2 will have So if you have a delay, this is not delayed. This is delayed by 1 delta t, twice delta t. This is here by 1 delta t plus delta t, so by 2. So I may write down here, if you don't agree, just let me know, e to the minus j twice n omega delta t. This is here the delay. I called it omega t or omega delta t or k delta x, but k delta x now is irrelevant for us. I think we slowly start to have a nice form. For those of you who have already dealt with signal processing, yes, you would like to ask? Excuse me? Rn, sorry. So thanks. Look now, we have a nice form. And the form itself tells me that this is R of omega. So let me okay. If you look here, how many unknowns are we looking for? No, actually we look for only for Rn. This is a formal argument. Delta t, it was my invention. We will show later this is a resolution with which I am reconstructing. But delta t, I say, okay, as I draw the profile, I draw it from my head. It could be no profile at all. So we could have just two materia, epsilon naught and epsilon 1, or two steps, or 3 steps, 100 steps. So this delta t equally spaced, it was just introduced by me. I also introduced local reflection at each point. And we'll see now, if it is there, it is there. If it is not, we don't have a transition between two layers. The way of thinking, the approach is clear. So as you see here, you are looking for Rn. If you succeed to find Rn as being related to n, you can also know their location. Because if I have R100, I know that the location of the reflection causing R100 is 50, because we have here 20, 50 delta t, or 50 times 2 delta t, or 100 delta t away from the beginning. So just if I can have this vector, this Rn vector, I got it. Again, so I have an expression here, and if I look here to Rn, if I would be able to find a vector with R0, R1, R2, 3, 4, 5, up to Rn minus 1. Now I look. R0 exists, R1 not, R2 not, R3 not, R4 exists. So I know that after 4 times delta t, I have a interface. And now 5 doesn't exist, 6 up to 14, 15 exists. I know now that I have another step at 15. The idea is clear. If you don't understand, just let me know, because the rest depends greatly on that. You seem confused. Okay? Every one of you? So the assumptions we made are clear. Okay, because I'm looking for n unknowns, I must measure n times. Therefore, I decide now to define R bar n, as being R at omega n. And I am, let me call it M. And M equals 0, 1, until n minus 1. Is clear? So, and let us also assume, if this is our frequency axis, we can take omega naught here, omega naught plus delta omega, omega naught plus twice delta omega, and so on up to omega naught plus n minus 1 times delta omega. Now we have, how many frequencies do we have? Also equally spaced. We have omega naught, we have also n. So this is now we have measured at n distinct frequencies. Okay? Good. Let us now look back to the expression. Expression tells me Rm is summation n equals 0 to n minus 1, Rn e to the minus j twice n delta t, and I have here omega naught plus m delta omega. Because if you look here, you can correct me if you, this was the value of, this is the mth frequency. This is a background frequency or something like that. Now let us play with the expression a little bit. So we can say, okay, this is here n equals 0 to n minus 1, and I have here Rn e to the minus j twice n omega naught. And here, and this is minus j twice n m delta omega delta t. Look to this here. Slowly I'm coming to a very familiar expression, which is DFT. If I am allowed to choose twice delta omega delta t as twice pi over n. Delta omega is in my hand, delta t is in my hand. Everything was, we are experimenting. So I will take the product of delta t times delta omega times 2 equals to twice pi over n. By the way, n is also my invention. Right? Put this together, you will have now the very, very nice expression, which is Rm is summation n equals 0 to n minus 1. Let me also call this one here Rn tilde, just because of this here, and I will relax this a little bit. So we have now Rn tilde e to the minus j, and now you have the nice expression nm twice pi over n. If you measure this, can you find this? Where are the signal processing guys? This is DFT. So if I tell you now that Rn is 1 over n summation m equals 0 to n minus 1 of what you measured, Rm e to the plus j n m twice pi over n. Will you believe me? This is the DFT, IDFT. This is DFT, and for those who are acquainted, or if you don't believe, give it to MATLAB. It's your friend. Compute or measure the RM bar, put it in a vector, and give it to MATLAB, and tell it please find the IDFT. Have we solved the imaging problem now? I will come now to more details about the choice of delta t, choice of delta omega, effect of resolution, and all this. But principally, I may claim we derive together a very simple expression for retrieving at least, in principle at least, approximate profile. You measure at m different frequencies. Of course, you can, when you know everything, you can find now, let me write down, how have we defined Rn tilde? It was just by Rn times e to the minus j twice n omega naught. Okay, let me now find the expression for Rn in order to be complete. We have Rn is e to the plus j twice n omega naught. What was it? Delta t? I think we missed here delta t. So, I can claim now that with these very, very simple direct thoughts, we have a mean for just measuring at n, capital N, different frequencies outside the stratification. And from that, we get the profile, at least within the framework of our approximations. What are our approximations? Number one, low contrast. We can detect that afterwards. If we find R is 0.5, one of these RNs, okay, without bar, it is not small reflection. But if it is 0.1, 0.2, and so on, it is small reflection. The other approximation, I defined delta t and I pushed the actual reflection to the nearest interface. So this is also an approximation in order to have this nice expression. That's all. And based on that, at least in principle, we have the initial guess, which we can give it to a more accurate software tool, which will finalize this to us. I will first discuss with you how can we retrieve the real thicknesses before, maybe in the next lecture, before discussing the effects of how big delta t, how big delta omega, and so on. Imagine now that to find that R0 exists, R1 equals R2 equals R3 to R7 equals 0, and then R8, I give just example, exists, and then R9 equals R10 equals up to say R20 equals 0, and then R21 exists, and so on. Now, because you know the location of every individual Rn, now you can have your initial profile. This is epsilon r of t, and now you have here epsilon naught. Of course, if you know r, you can find epsilon. right? Because what is R? Rn was. We called it here 0 was 1 minus 0 divided by 1 plus 0. So I take actually Zn plus 1 minus Zn divided by Zn plus 1 plus Zn. If you, because you start with 0, you can find dielectric constant 1. Knowing 1, I can find 2. Knowing 2, I can find 3, and so on. So actually, now you have the profile as a function. Say this is T1. This is T2. Of course, T1 here is not after just 1 delta T. I skip now all zeros, and now I pick up only the non-vanishing deltas, and I construct now, maybe this is, I will say, maybe this corresponds, based on that here, corresponds to R8. This one here corresponds to R21, I think. Yes. And so on. Just an example. Please don't take this as a wholly. So I just made some examples. Okay. So we'll end our lecture today, or at least now, by how can I retrieve the x's in terms of t's. Okay, let us see. How can I write down t? Let me take another color. We have t n minus t n minus 1 was equal here c naught, and here square root of epsilon r. I think we get n here times xn minus xn minus 1. Was it so? Let us see. Okay. So we have n here. Let us try to write down this as a matrix equation. Let us have T naught. We have the first one, T naught is 0. Yes, T1. T naught is 0, but let us have it as a T naught. I would like to write down this equation as two matrix equations. We have the first one, a relation between T1 and T0, in which T1 has plus 1 and T0 has minus 1, and the rest is 0. And I have here square root of epsilon r1 times c naught. Let me write it. The coefficient, the difference between the coefficient of x minus 1 and x n, once is minus 1 and once is plus 1. So we will have here minus. I will not write down this this one here, because so I will write minus and plus, and this is actually referred to this here because I don't have enough space. That's all. And then we have 0. In the second equation, we have 0 minus 1 plus 1, and we have here 0 minus plus 0, 0, 0. Can you complete the matrix? I think it is systematic. And don't forget, from the R's, I already know the epsilons. So these coefficients here, epsilon R1, epsilon R2, and so on. Okay? Can you get the x's now in one shot? Yes, because if I need x's, I have the t's. I will take this matrix, invert it. The matrix itself is nice because it is not a diagonal matrix. It is not triagonal. You know, diagonal is one diagonal. Triagonal is 3. It is a triagonal, but one of the third one is zeros. So it is half upper matrix with the main diagonal and one side diagonal. If you look, if you don't want to do it by yourself, ask Google or ask MATLAB, and you have extra programs for such special types of matrices. You don't need to put it as a general matrix, because for diagonal matrices, for 3 diagonal, for triangular matrices, for what is called circulant matrices, there are many forms which you don't really need to use general purpose inverting program. So you may use, you may find the inverse by yourself. I don't have it now in my mind, but I know such simple structures of the matrices are easily inverted. If you are not content with that, you can also work iteratively, because if you look here, I have epsilon naught and epsilon 1, and I have t naught and t1 and x naught. From the expression that t1 minus t naught is equal square root of epsilon r, let me write it down here, only step by step. So you may say t1 minus t naught, which is actually 0, is square root of epsilon r1 divided by c naught in x1 minus x naught. Okay? This is known, this is known, this is known, and this is known. This is the only one unknown. You can find x1 if you don't want to invert matrices. Now go to the next step. T2 is known, T1 is known, x1 is known, epsilon r2 is known. You can find x2 and so on. So if the matrix inversion is not nice for you. So I believe that with this we find the first analytic form of retrieving a permittivity profile based on small reflection, number one, based on sacrificing some resolution, because the interfaces I'm getting here plus or minus half delta t, because I can have pushed it this way or this way, so I have a tolerance of delta t, and this belongs to my resolution. But don't forget that I put delta t by myself. It is in my hand. But we will see when we return back 2 o'clock with which price do we pay in order to increase the resolution, in order to make this delta t as small as possible. Do you have any question before finalizing this? So can we finish now and then we meet 2 o'clock? Okay, so thank you.